Hello everyone, welcome to the mobile graphic best practice for artists session. I am Owen from ARM. I am the developer relation engineer at ARM. Today I am going to talk about the following 4 topics about mobile graphics, including texturing, geometry, shader, and frame rendering. And at the final slide, I will also list a few online resources. You can check it later. So let's start from texturing. Trilinear filtering. So trilinear filtering is just like a bilinear filtering, but with added blur between Midmap data. So you can generate a better image quality than bilinear filtering. But since it access to Midmap data, so make sure you use it with Midmap data. And the trilinear filtering can remove a noticeable change between Midmap levels by adding smooth transitions. But trilinear filtering is still expensive on mobile because it will cost 2 times longer to get the data back to get the data back from compared to bilinear filtering. So you should use it with caution. Only use it in critical area. So next one, isotropic filtering. Isotropic filtering is another way to sampling texture, and it will make texture looks better from different angles, and is especially good for grounder level texturing. And you can using isotropic filtering, you can choose different level of isotropic filtering. Higher level can generate higher, better quality, image quality, but it will also cost higher. So the best practice of textual filtering. Bilinear filtering is still your best choice because it has a good balance between image quality and performance. Trilinear filtering will cost more memory bandwidth than bilinear filtering, and it need to be used very carefully. You should only use it on very critical gain asset. And bilinear filtering plus level 2 isotropic filtering at the most time has better looks better and performs better than just use trilinear filtering, because this combination has less sampling than trilinear filtering, so it performs better and also require less memory bandwidth. So this combination can be a better solution than just using trilinear filtering. And if you have to use trilinear filtering, please remember to keep the level as low as possible. Usually you should keep this isotropic level lower than 2, because if you higher than 2, then you will cost a lot of memory bandwidth and get worse battery life. So next one, always use Midmap if camera is not still. Using Midmap can improve GPU performance because it can reduce the cache miss, and the cache miss also mean less memory bandwidth, and the less memory bandwidth means you can get a better battery life. And Midmap also can remove texture aliasing. And improve the final image quality. But remember, don't use it on 2D objects like UI. You should only use it on 3D objects. And next one, texture color space. In Unity, there are actually two different texture color space, gamma space and the linear space. So if you are using dynamic lighting, real-time lighting for your game, then you should choose to use linear space to get the correct lighting result. And in Unity, how to enable it in Unity, you can check sRGB option in texture inspector window to use linear color space. But non-color texture should not use linear space, linear color space, because linear color space is only used for color texture. For texture like a normal map or smoothness map is a kind of data, not color. So you should not use linear color space. And when you choose to use linear color space, then Unity will create sRGB format. And the current most modern GPU support sRGB, so the hardware can do the gamma correction automatically for free. Texture compression. As you can see from the picture, STC usually get better quality with the same memory size of ETC, or ASTC get same image quality but smaller memory size than ETC. But STC will take longer to compress, so it may make your game building time become longer. So it's better to use STC at the final package of your game. And STC allow more control on image quality, because you can choose different block size. And there is no single best setting for block size, but usually, generally, 5x5 or 6x6 is a good setting, good default setting for most kind of texture. But you can try different block size to get the best result of STC. And currently, all Mali GPU after T620 all support STC format. So next one, texture channel packing. Texture channel packing is a simple but useful technique to improve your game performance and reduce the memory bandwidth. It means you can use texture channels to pack multiple texture into one texture. So in shader, the texture fetching instruction can fetch the data just in one instruction. And we all know the GPU will fetch the texture data, fetch 4 component data at once. So if you are just using 2 or 3 components, that means you just use a 2 or 3 channel of texture. It's a kind of waste the memory bandwidth. So that's why we need to we can use texture channel packing to improve the performance and also save the memory bandwidth. And it is common to pack like normal maps, roughness map into one texture, but you actually can pack any kind of a texture mask into one texture. So next one, geometry. The first one, avoid rendering small triangles. Rendering small triangle is bad for mobile GPU because the bandwidth and the processing cost of vertex shader is much higher than the cost of fragment shader. So make sure that all primitives you rendered covers enough fragments, so the vertex processing is worth. But for 3D game, the objects which are further away from the camera will become smaller, and the triangle or the primitive will become smaller. So in this case, it is important to use mesh level of detail to 3D objects. So mesh level of detail means you are going to use a simpler model for the objects which are further away from the camera. And the most important thing is you should make each model generate at least 10 to 20 fragments per primitive. And the next one, avoid rendering long thin triangles. We just say it is bad for mobile GPU to render small triangles, but render long thin triangle is also bad for mobile GPU because GPU process pixels in quad blocks. So if you are rendering long thin triangles, there will be a lot of GPU power waste. That's because AV triangle edges have some pixels in the quad will be discarded after rasterization. So you are spending GPU power on those discarded pixel rasterization. And longer edges also means there are more pixels are discarded. Then you will waste a lot of GPU on processing those pixels. They are eventually will be discarded. So we can see. Let's see the example on the picture. On the left side, the mesh layout of the left is the worst because it has the longest edge. In the mesh layout in the middle is better, but the mesh layout in the right is the best because it has the shortest triangle edges. And the next one, avoid duplicating vertices. Avoid the duplicating vertices unless it's necessary. Otherwise, you should reduce your vertices as many as possible. So why? That's because the GPU will cache the transformed vertex data, then fetch it directly when following triangle reuse it. So it can save vertex processing power and also save the memory bandwidth because the GPU fetch less data from vertex buffer. And the next one, instancing. Instancing means you are rendering a lot of object with the same mesh but different properties for each instance. For example, you can use it to render a lot of trees or rocks. They are pretty much the same mesh but with different scale, position, and rotations. And the advantage of using instancing is that you can you can reduce the number of draw calls, and you also can reduce the requirement of memory bandwidth because you just need one mesh data. You don't need a lot of duplicate mesh vertex data. So how to use it? first you need to check the enable GPU instancing option in material window. Then you can use the Unity access instance the property function in shader to access the property of each instance. So the next one is about shaders. The first one is about floating point precision. On mobile GPU, medium P and high P actually has different size. Medium P is 16-bit and high P is 32-bit. So you need to explicitly use medium P or high P keyword to tell the shader compiler which size you are going to use. And the processing speed is also different. The processing speed of medium P is twice faster than the speed of processing high P. So you should use high P whenever you need to use it. For example, computing vertex position, you can use high P because it needs a higher precision. But for color and the textual coordinate, you should probably only use medium P. And don't use high P for everything. It probably okay on desktop, but it will be an issue on mobile GPU. So remember, just use high P whenever you are sure you need to use high precision floating point. And the other thing is don't upload your data don't upload high P data to a buffer, then read it back as a medium P. In this case, you just waste the memory bandwidth to read the data in and discard the precision part. And the take advantage of RZ. All modern GPU suppose RZ. RZ means that on screen there are actually a lot of pixels are occluded by other pixels. So GPU actually can find those occluded pixels then before running fragment shader, then kill them directly. So we can save a lot of fragment processing power on those invisible fragment, because this occluded fragment will not contribute to the final image. But RZ can only works on opaque objects, and this feature will be turned off if you are using discard instruction in shader, or you are writing depth data into depth buffer in shader, and it will also be turned off if alpha to coverage feature is enabled. So I just say RZ only works for opaque objects. So for the fragments that are using alpha tested or blending, testing or blending, they cannot take advantage of RZ. So you for optimization, you should try to reduce the amount of this kind of fragments. And I will talk about how to do it later. The next one, avoid the heavy overdraw. Overdraw means that one pixel has been rendered over more than once. So higher overdraw also means worse performance. And the overdraw for the alpha blending or testing, not testing, for alpha blending fragment is more expensive because there will be some pixel dependency to slow down the pipeline. And in Unity, you can use a Unity built-in display feature to check the amount of overdraw like the pixel shows. And you can see from the picture, the brighter area means more overdraw. And how to reduce the overdraw? You need to render objects in front to back order. So in this order, we just mentioned the RZ. The RZ can help you to kill all the fragments that are occluded, so you can save a lot of fragment power on rendering. So in Unity, you need to make a good arrangement of the layer, sorting layer, and the render queue, and the camera setting to make sure you render most objects from front to back order. And the next one, reduce the amount of alpha blending tested fragments. I just said alpha testing and blending fragment are expensive for mobile GPU because it cannot take advantage of RZ. So we need to reduce the amount of this kind of fragment to get the best performance. There are two ways to do that. The first one is separate the transparent mesh from opaque mesh, like the left image shows. So by doing this, you are reducing the total alpha tested or alpha blended fragment. And the second one, you can use polygon mesh instead of quad for transparent texture, like the right picture shows. Both ways, you reduce the amount of the fragment, and you can improve the performance. Dynamic branching. Many developers think dynamic branching is very expensive, but actually it's not. It's not expensive, but but in some situations it could be very expensive. Because if you are branching in very small area, then both sides of branch will be executed, and just pick one. So you just waste one side power to compute the data that will be discarded. But this situation is rare. So don't worry too much about it. And the current shader compiler can optimize the branch automatically for you. So at the most situation, dynamic branch in shader is not as expensive as you may think. But just make sure when you are using a dynamic branch, you need to make sure you use it to skip enough computations. So next one is about the frame rendering. It's about how you render a whole frame. First one is a reduce render state switch. Many developer knows draw code is expensive, so they are trying to reduce the number of draw code, but actually the render state switch is also a very expensive operation. So how to improve the performance, you need to make sure you can render as many primitives as possible before you switch render state. So remember, not only check the number of draw codes, but also check the number of render state switch as well. And you can check how many triangles are rendered per set pass to make sure you render enough triangle before render state switch. In this example, you can see they are 95K triangle has been rendered, and there are 34 set pass. So 95K divided by 34 is about 2.8K triangles were rendered per render state change or per state pass. So in order to reduce a render state switch, you need to batch your draw code as many as possible. So static batching, dynamic batching, and the GPU instancing all can help you to reduce the render state switch. And next one, reduce frame buffer switch. A mobile GPU render buffer switch is kind of expensive. It will cost a lot of memory bandwidth. So you should buy the frame buffer only once and make all required rendering at once, then switch to the next frame buffer. And it's pretty bad for performance if you are rendering in one frame buffer, then switch it to another one, then bind back to the origin frame buffer, then do the following rendering. And this is a very bad behavior because they will a lot of unnecessary memory bandwidth cost. So reduce frame buffer switch can also reduce memory bandwidth requirement and get you a better power consumption. So remember to render all your required rendering before you switch to another frame buffer. And clear frame buffer before rendering. So on mobile GPU, before rendering, the GPU will read the frame buffer data, list the frame buffer data from into the GPU from external memory. So it will cost some memory bandwidth to do it. So the application should try to minimize the memory load when render pass start. So how to do that? You can actually cheaply initialize the tile memory to the clear color value by coding clear before rendering. So if you know you are going to redraw the whole screen and you don't care about the data of the last frame, please remember to code clear before rendering. Then it will save you a lot of memory bandwidth. And we just say there are some memory bandwidth requirement before rendering, and there are also some memory bandwidth requirement for after rendering. So the mobile GPU need to write the result from GPU to external memory at the end of the render pass. So the application should also try to minimize this kind of store operation to save memory bandwidth. So for example, how you can minimize this kind of operation. For example, if you are rendering 2D like UI, you don't need the depth buffer. Don't bind it. If you don't bind then GPU will not write the result back to external memory. And if you are if you know you are not going to use the depth data at the next frame, so you can just discard the current depth data, right? So at this situation, you can call render texture discard contents function to tell the tell Unity to invalidate the frame data. Then GPU will not write the result back to the external memory. Okay, resources. Here are some online resources you can check later. They are all about mobile graphic optimization, and then they are very useful. It's online and it's free, so please check it. And you can. We also just released a free tool called OnMobile Studio. It is used for optimize your game performance, and you can actually download it for free now and use it to improve your performance, your game performance immediately. And we also have a new tool called Performance Advisor. Is a automatic tool. It can generate a performance report for your game automatically, so you can integrate it into your CI system. Okay, so that's pretty much all for my session today, and thank you for your joining. Hopefully you will find it helpful. And if you have any more questions about Mali GPU, please feel free to contact with me or on Developer via email. The email you can see from the slide. And thank you for your joining. Thanks.